Okay, I think we can start. Angelica, the floor is yours.
I think yes. So I hope you had a nice lunch break. It's not easy to be back after the lunch, especially if you look at outside. But now I guess that we have to start with the session 3. And we are moving from this morning that we were talking about future. We are now talking about the present and the experience of multi-particle therapy facilities in operation in Europe. And the first speaker is Konrad Lehmann from GSI. He is a senior researcher there at GSI and is going to talk about hadron therapy at GSI, where we come from and where we go. Thank you, Konrad.
Yeah,
I'll do it. Okay. Okay, thanks for the introduction. In fact, I'm very much senior, but not a researcher, in fact, but we already know that. Yeah, thanks for being here. And okay, I hope you will indulge me if I treat you to yet another bit of history, because after all, if it comes to hadron therapy at GSI, we are history. And basically all, if anything new, yeah, no reaction whatsoever, not even here. No, no, okay. Okay, so it all started with this guy, Pierre, the thing who most of you know, who unfortunately passed away 1.5 years ago, somewhat unnecessarily. And he, during his time at Berkeley, came across the idea of hadron therapy, which, as you know, didn't quite make it into clinical implementation there. But when he came back to GSI, he still had this idea this might be how this could be made to work. GSI at the time was a purely physicist institution. They used the iron beam to create all these heavy elements which decay after milliseconds. Gerhard, in fact, had the power and the inspiration to make all these physicists do something useful for a change and jazz up the accelerator in such a way that for example, energy changing times could be done from minutes to mere seconds. You develop the detectors and all of this to, in the end, make it really work. And yeah, these are some of the instruments which developed this or were used in this during time. You see with the steering magnets. This is the detector set up, and this is yeah, the nozzle look like this is the PET detector they used, and the nozzle of the beam of the original facility at KFM and GSI. And the result of all of this then was, as you know, I think you've seen this image already in Sanya's talk, so I can be very brief here. Without was that beam could be used to do a 3D scanning of tumor of any size you wish and give a uniform dose to every position in this tumor, and thereby destroy the tumor within the tissue, the body, without doing too much damage to the healthy tissue around it. And just to show you all this effective as well, and here's this was some old images, just history, as I told you. So this is not a real patient. It might even be because Harper, I'm not quite sure. But just to demonstrate the setup to the original one, and here again, this is what it looked like. It doesn't look like this anymore because, as I'll tell you in a few minutes, science has been moving on, and we have just been refurbishing this cave a bit to do some more state-of-the-art research there. Yeah, and the result then was between 1997 and 2008, we treated 434 patients there. Just show you how effective this was, and we read at the time some early papers from one of Gerhard's first evaluative assessment papers of the research that shows effectiveness of tumor control in a third of these patients who had a chondrosarcoma or chordoma. You see the tumor control across 4 to 5 years was pretty good. 100% for chondrosarcomas and some 80% for choromas. Somewhat later assessment showed that even though a much longer time, this here, you can't read it, but this is 15 years. It's I think 180 months or something. And you still have, this is survival, if I'm not mistaken, survival of 80% over 15 years. I mean, some of us won't be here in 15 years even without having cancer. So this is pretty good. More long-term, well, let me go back as an option here. Okay, but what I want to say is, and of course, nice if it is effective, but in the clinic, the important question is it more effective than what we had before? So the valid comparison is with X-rays or protons. And this is what's shown here. This figure is a bit of a mess, I must say, dear colleagues from Heidelberg. All these dotted lines are in 95 confidence intervals. So the comparison is between the blue line for carbon and the green line for photons. And you see the 15-year survival curve is notably and probably significantly higher for the carbon-treated patients in hadron cystic carcinoma. I get a similar image like this also before already today, showing that if the effect of those and the probability for X-ray protons and carbon ions. You see that carbon ions are way more effective even than protons in treatment. So this was altogether a success story, with the consequence that even while this pilot project at GSI was still running, we were starting to build the Heidelberg Ion Therapy Center. And since then, we have continued to proliferate. You've seen similar maps as this before. Here again, managed Europe is in the center. I beg your pardon, I just got it from the internet. And this is only the carbon facilities. So if I had added as well the proton facilities you see before, I would have had a lot more work to do. You see, it's still a bit clustered. So we have at the right is the Darmstadt. The resolution is not very good. Red is Darmstadt. Yellow, orange are existing facilities, and green are the 3 ones which are just currently under construction. It's very clustered, so we have a big hub in Central Europe and a big one in Japan, and a lot of white space around the world, which needs filling. I think we all agree. Now, this is sort of basically where we are now, and now this was the history part, and it was very quick, I say, but science never ends. And I'd like to tell you a bit about what we're doing at GSI right now. There's a lot of interesting projects going on, and I've decided to focus a bit on these 3 for the purely personal idiosyncratic reasons. And these are the ones that I understand best. Well, if you're neuroscientists, and these projects at the moment involve animals that understand, well, all the other projects are certainly in no way inferior. Don't imagine this. So I think one of the more hottest topics in radiotherapy research nowadays, as you all agree, is flash, which was first discovered in X-rays, and is the fact that if you deliver your irradiation with a very high dose rate in a very short frame of time, you have the equal tumor control, but spare the healthy tissue a lot better than with normal low dose rates. This could easily be adapted then for protons and cyclotrons, but it was a bit tricky with heavy ions. It was again at GSI in collaboration with HIT in Heidelberg intervention that we managed to jazz up the accelerator to do it with heavy ions 3 years ago. And the same year, we also first did it in experimental animals, so this in mice, injected them with tumors in the hind limb, and used flash carbon ion irradiation to treat this tumor. And well, to show you the results shortly, first we had to overcome some problems. One problem is that with flash irradiation, the scanning time is so short because the dose rate is so high that scanning the tumor is not really an option. And this is mostly work of Uli Weber with colleagues. He developed this range modulator, which allows to, this is a simple rack peak as we know it. You send it through the range modulator, which looks something like this. Here it's a spherical one, and the effect then is an equal dose distribution over the shape of the range modulator. And you can give the range modulator any shape. So here you have this kind of a somewhat naturally shaped tumor, and then you make a range modulator of the same shape, and then you can treat with one shot this tumor in flash treatment. And I come back to the animals. So we did carbon flash in mice. That has already been published. So Paganelli is the principal investigator here within his group. And you see in this paper, they show that there's tumor control, comparison of this tumor growth over time of 4 weeks. And the sham-irradiated animals, of course, it grows until the animals have to be sacrificed. Whereas with conventional treatment and flash treatment, you control the tumor quite effectively. And indeed, this was unexpected, and we need to see whether it gets confirmed. Would not be the most important thing, but would be nice. Indeed, flash treatment even controlled the tumor better than conventional treatment. The main hallmark of flash effect, as I told you, however, is the sparing of healthy tissue. And this here in the central panel, where muscle tissue damage was assessed in 4 steps. And you see that sham irradiation, of course, muscle is fine. What else? And with conventional dose rate in all the mice, the muscles have shown considerable histological damage, which is significantly much less, even partly absent in the flash treated mice. And another unexpected effect is shown on the right. We used a cell line, LMH cells, and LM stands for lung metastasis. So it's a cell line which forms a tumor, but also metastasizes very strongly. And they then took out the lungs afterwards and assessed the number of, or area, in fact, of metastasis in percentage of area. And you see that it's, of course, highest in sham-treated animals and no significance with conventional dose rate, but in the flash-treated animals, the number of metastases in the lung is highly significantly greatly reduced, which shows that there are abscopal effects which we are currently doing further research. The next very fanciful, very fascinating project I would like to briefly say about is BARB, done in big collaboration with many other researchers. Very important part is done by Katja Barodi in the group in the LMU in Munich, which tackles the problem of monitoring the treatment locations or the beam where the beam ends up. And the point is that if you show here and this standard carbon, and you can do a treatment with often circular, as a simulation, of course, a tumor or something, and then the decay of what's called the protons which are created are being used for a PET image to see whether they really had the tumor. And this works, but the signal, as you see, is rather weak, so you can't really do an online monitoring, but just to collect some signal and then wait some minutes until you get a reasonable image. But it's not really useful for online at the moment imaging. Whereas if you could use a radioactive beam, so if you could, instead of carbon-12, could use carbon-11, you could just do perfectly the same treatment, but the decay signal, of course, would be much, much stronger, and you could really use it for a very strong PET imaging of the tumor. And this is right now ongoing work. Last year had first we had to set up the fragment separator to separate the carbon-11 from the carbon-12 and get all of this doing such. Nothing which will make its way in the clinic in the next year, certainly. It's not easy, but we managed. And so last year we traded our first mice with radioactive carbon beam, and Katja provided us with this very nicely looking simul PET scanner for small animals. So this is, you can see here a mouse in this holder, which is then inserted here into the PET scanner, and the beam nozzle is behind this, and then we treated a tumor in the back of the neck of the animal, because the idea is that if you are near the spinal cord, then we can see whether if we are able to shoot more precisely, we can spare more of the spinal cord and get less neurological damage and locomotor impairments. This is ongoing work, and this is working very fine. Something which my colleague Olga Sokol already presented, I think the PDCOG, is this last point, the washout. This is a very nice idea by Marco Durante, that if a high dose of radiation destroys the vascularization in the tumor, then washout of the radioactive signal should be delayed, and then we could have a direct assessment of the damage to the vasculature, and it has worked, but not going to show the data because I'm a bit running out of time anyway. Just briefly, the ongoing project of my colleague Christian Graf. Again, on the issue of range uncertainty and beam monitoring, the idea to make this bit brief is to use a carbon beam, but mix 10% of helium inside. Helium, being lighter, has the same energy in greater range, so it will just pass through the body. And then if you put a detector in the beam line behind it, you can use the helium for imaging to recalculate where the carbon has stopped. And this is ongoing. The first experiments last year, from the physical experiments without mice, and there's some work which is now being done. Christian has published a bit about it. So it is working, and we'll be using some. And everybody nowadays, some artificial intelligence to figure them out, the signal here in the detector in the end. Just briefly, the other things we're doing, just to show you how much is going on. Christian is also working on the issue of how to hit moving targets, like when you have a tumor in the lung or anywhere in the breast. We're also working on improved treatment planning methods. Claudia Fournier is working on the immune system involvement, also in nano experiments right now. A funny little thing we're doing, or the Walters group, is we try to induce a torpor-like state, like hibernation in mice, because the lower temperature damage to the healthy tissue might be reduced, and also tumor growth might be reduced anyway, and then we might have better tumor control in mice in torpor state. It's a bit tricky, but it's also ongoing work and will be continued next year and during beam time. So this is what we're doing. These are the people who are doing it. So we are at GSI currently 86 people. But it's quite remarkable if you know that Gerhard started off without even their own work group. He was a physicist, and built all this up, and Marco continues to build it up. We have a majority of women there. People from all over the world. We have the feeling that most are from Italy, which is not quite true, but many are. We are a very young group altogether, and very, very nice to be with. There's several work groups. Touched on the research of some of them, like Uli, Christian, Walter. Claudia's doing immunology. Charlie has just started space radiation lab, which is investigating the alteration of the microbiome and then the influence of space radiation. Doing space radiation physics. Insa is doing very nice things on brain organoids, which is appealing to me as a neuroscientist. And Burkhard is doing a lot goes down to the core of the things, to the DNA repair after damage by the iron beam. So these are the basic our two legs we're standing on. So it's not a big part of it is particle therapy, but we also have always been doing some space radiation research. within this case we're using. So this is the original cave, and as I said, this is being changed as we're talking here, and cave A for more of the basic science experiments. It's going on, and right now they are building the new FAIR facility, FAIR for Facility for Antiproton and Ion Research, which will be a much bigger accelerator of 100 meters in diameter. This is what it's supposed to look like when it's ready. So here is the original GSI, and all of this area here is the FAIR facility, which is supposed to be ready in 2028, as far as I know. Let's hope it really works out. And more they are on time, as far as I know. And this is from April of this year. This is what it looks like at the moment. It's so this has made some progress, but you see the rings is built. They're bringing in the magnets, so have been bringing them. Right now, they're doing a lot of earthworks outside, and always sometimes walking over there in lunch break and have a look at what it looks like. So hopefully, in a few years' time, we will have a lot more time than we have now, which is an issue, and much better and stronger facility, and the ability to do a lot of even more fascinating research. I think Jutta asked me to do a few final words on the involvement of GSI and the H3 Plus Consortium, because out of all the Hadron Research and Therapy Centers in Europe, where we are offering transnational access hours with the ability of both researchers in the one branch and of clinicians in the other branch to be guests at our facilities. The research facilities is GSI, HIT, and CNAU, welcome guest research TNA hours, and especially here, I think there are some physicians present. I encourage you to apply for clinical TNA, which is the possibility to have a patient sent to one of the clinic facilities and also get travel by the accompanying physician paid. It's a great opportunity to have people from countries which currently still don't have their own accelerators being treated with state-of-the-art carbon therapy. If they should be interested in any of the branches in getting research beam time or clinical patient there, then apply by our website. Yes, and that's all. This is all I wanted to say, but there was one remark I wanted to make at the end. I wanted to make it earlier, but I forgot. It is that you remember that GSI was created to make all these heavy ions, these heavy elements, which nowadays form the bottom line of the periodic table of elements. I think half of this bottom line are from us. It's worth noting that quite probably right now in all of the universe, there's not a single atom of Darmstadtium, whereas there's on this planet alone a few tens of thousands of people who have been treated with ion beams and have survived and have their lives improved by this treatment. So this really shows how physics can be put into good use. And with that, thanks for your attention.
Thank you very much, Konrad. There is a comment from online saying it's related to flash. I don't know if it's from you, but it's a comment saying target fragmentation effect will be larger in flash therapy as large flux is transmitted. I don't know if it's a question for you or a comment for the...
I'm not a physicist, I couldn't really say anything about it. Maybe it's just a comment. If anybody wants to contribute to that.
If you want to say something. I mean, is there any questions there in the... Okay, wonder.
My question is, so you are using C11 for the irradiation of mice, yeah? What is the intensity of the source? How strong beam are you able to produce with C11? Is it like that you can normally then provide it for carbon ion therapy? It's so efficient, or it is just
I couldn't tell you exactly, of course, but I think so, because we did treat the mice with it and we achieved tumor control.
yeah, but it's a very small volume. Yeah, of
It is
course,
for mice.
it's a few centimeters. Yeah,
Yeah.
okay.
Okay.
The idea of the carbon 11 is really very nice. I was just wondering, assuming you have carbon 11 for treatment, would that need a synchrotron or a fragment separator?
As far as I know, there are, in theory, different ways of producing a CC11 beam, but yes, we're using fragment separator, and yes, we'll certainly use a synchrotron. So certainly nothing which you would implement in the clinic in the very near future.
And why not using the carbon 11 through a cyclotron and then accelerating this?
I think I'm overtaxed with that question. I'm not a physicist, but
No, I was just wondering, loudly. Yeah. Because carbon 11, you do that for with radiopharmaceuticals, but
Yeah, but probably you are not producing a pure carbon 11, it can be separated.
it also has to do with the half-life of carbon. I think it's very short, so you
it's really short.
get used to.
But I just imagine to have a fragment separator in a future hardware facility. This will. I mean, I can hardly. Sorry.
Certainly.
Konrad, I have a question. I mean, maybe I didn't catch during your presentation, but the new facility, what will you be able to do more than that you are already able to do with the previous one?
I don't think it at the moment makes much of a difference for us in biophysics. I think the physicists can be very happy about it.
Okay.
I don't
Sorry
know,
for
for us, and I don't know whether we need antiprotons. Yes, yeah, that's where, of course, that's why it's the answer for the antiproton and ion research. So yes, but I'm not sure whether we will need antiprotons for treatment. I think we'll be happy when it's done, because then we will get more beam time in our case, and we get some experience rooms there as well.
Okay. Any other question for the GSI? Okay. Thank you. Thank you very much.
Thanks.
Okay, now we can move to the second facility that